So this is a part of physics which is not what I am working on, but what I can say a few things about that. If you have different forces in nature. The electromagnetic forces are the one which hold the nucleus, which has a positive charge to the electron, and this is a force which is long distance. In fact, this electromagnetic force can act at very, very large distances. It decreases with the distance, but as a 1/r² law. The forces which hold the particles inside the nucleus are much short-range forces. And what defines the range of, in fact, forces, what quantum physics tells us is that forces are related to the exchange of particles, which are the carrier of the force, and these particles are called bosons. And for instance, the electromagnetic force is produced by an exchange of photons, and the photon is a special case of boson. And the force is a very long distance force because the photon has zero mass, so it can propagate over a very long distance. The forces which hold the nuclei together basically are very short term, and they are due to exchange of massive particles, which are called gluons, and which can propagate only over very short distances. And the model of matter, which is now the accepted model and which explains how the subatomic particle work and exert forces on each other, is called the standard model of quantum physics. It works very well, and it has unified, it allows us to understand the nuclear forces, short-range nuclear forces, the electromagnetic force, and also the force which is related to radioactivity, which is called the weak force. These three forces are embedded into a unified model which works very well. One force which is still out of this model is the gravitation. One does not know, one doesn't have a quantum theory of gravitation. Beyond that, I think it becomes more complicated to discuss, but what particle physicists are doing is trying to understand better the forces at the subatomic particle level, and you know that the latest discovery at CERN was the discovery of one more boson, the Higgs boson, which is very important to a particle which explains how the different particles of the standard model have acquired their mass. Because at the start, the theory predicted particles which had no masses, and of course it's not what we observe in nature.
We have a surprise. We got the sponsorship for a brand new microscope that we can give away today, and I have got all the schools' names in here, and we're just going to have a lovely go.
Okay. I have to go. I take one.